This question is asking which of these two pictures would show the correct situation. This is called a Venturi meter. There's some sort of like airflow on top here, and the airflow gets constricted to a smaller region here. Then at the bottom, this stuff is a fluid, and a fluid has a much larger density than the air. So the question is, given the large area to small area switch, would you see the fluid have a higher right side or a higher left side? So let's go through and figure out the details of the problem so we can decide which picture is correct. So first, I'd like you to think, how does the velocity through the big area compare to the air velocity through the smaller area? Right, so our stuff is flowing through and then gets constricted to a smaller area. How does that change the flow? V1 versus V2. Okay, same things happening on this picture. Then I'd like us to think about the pressure in each one of these locations. So the pressure in this part of the container won't be the same as this part of the container. So I'd like you to compare our P1s and P2s. From there, we can go ahead and think about hydrostatic equilibrium in the bottom part of our tube where things aren't really flowing. So in the bottom part of our tube, this P bottom, we can use statics. So we can say the pressure at this location and the pressure at this location must be the same. But on one side, you're going to have that pressure plus rho GH, depending on which side we're talking about. Now, here's the mistake that I did in the last video. I included the fact that the pressure in this column matters. And at our level of physics, we just ignore that because it's usually such a large difference in densities that this pressure and this pressure are pretty much the same, just like we ignore the buoyant force in the air. So that was my mistake, is that the density in the lighter, the pressure in the lower density side is just going to be considered uniform. So you don't have to worry about a rho GH on the lower density side. Just a heads up there. Okay, so back to it. Let's compare our velocities. So using continuity, right, we're going to be able to answer about our velocities. So you'll have A1, V1, and that needs to equal A2, V2. From this, you'll conclude that the velocity in 1 is less than the velocity on side 2. Okay, from there, we can write out Bernoulli's. P1 plus rho GY1 plus 1/2 rho V1 squared equals P2 plus rho GY2 plus 1/2 rho, 1/2 rho V2 squared. The y values of this location through the flow are the same, which will cancel these terms here. We can then say that our left side term is smaller than our right side term here. This term is bigger because our speed is bigger. Therefore, the pressure on the left side must be bigger, and the pressure on the right side must be smaller. So to write that out, we conclude that P1 is larger than P2. From there, we can use our P bottom. So P bottom, the bottom of this location for either tube, whichever one's the correct one, will have to equal the other side here. So P bottom, if we write it out for one tube, will be the bottom. Let's say the bottom is the same pressure as P2. If I wrote it out for this one, you'd have to say P2 would equal this spot right here. But that's on the bottom of this column. So that would say, oh, what's on top? P1 plus rho GH, the depth of the mercury. Or would we be saying, if we're looking at the other one being correct, that this is our P bottom here? And so P bottom is the same all the way across. So P bottom equals P2 is on top plus rho GH of the mercury column. And since P1 is greater than P2, this is the solution that makes sense, not this one. Okay, so I'll go through the example problem for you. Now we know that this is the example that makes sense. Continuity concludes. Okay, here's the example problem from below. So we have our two areas here, and in here there's water flowing. And now the assumption that we are going to make is that the pressure on the left side, whatever pressure is in here, is also in this column. This is the assumption I did not make when previously solving this. But it's fine, I guess, to make that assumption because the water is a lot less dense than mercury. So I'll show you the way the AP is going about it, and then I'll show you the way that we can be a little more detailed. So first, let's just use continuity. So A1 V1 equals A2 V2. Right, where we're going from the left side to the right side. So here, the first thing you can do is you can rewrite the A1 as 4A2 and put in your V2. It's 2 equals A2 V2. And so we find the speed on the right side comes out to be 8 meters per second. All right, so speed here is 2. This area is 4 times as small, so this speed is 8. All right, now let's go into Bernoulli's. So let's find the pressure on the left. Okay, when you write out Bernoulli's, the height here and here is the same, so you can get rid of these y2's. So you'll have P1 plus 1/2 rho V1 squared is P2 plus 1/2 rho V2 squared. And we know all of this business. So we'll say that this is P left, this is P on the right, and we can fill it in. So P on the left plus 1/2 the density of what's flowing, and the speed squared, equals the density on the right plus 1/2 what's flowing, and V squared, 8 squared. Okay, so you know that pressure difference between the left and the right, P left minus P right, is going to be 1/2 times 1,000 times 8 squared minus 2 squared. So I just did a little math all in one step. If you plug that in, that comes out to be 30,000 newtons per meter squared, or pascals. Okay, then we'll go into statics. So we'll say, all right, the pressure here is the same on this whole thing. So you'll say this is P on the left side. And that P left also needs to be equal over here. But what's going on here? On this side, there's this large column of mercury on top of you. So you'll say, well, what's on top of me? This large freaking column of mercury. So P on the left needs to equal this large column of mercury plus the density on top of it, P2. Or P right, I've been calling it. Okay, so then using statics, we can say that P on the left equals rho GH, this is of the mercury, plus P on the right. So let's go ahead and do some subtraction. So P on the left minus P on the right with statics is going to give us the density of mercury times gravity times the height, h. And you know what P on the left minus P on the right is from the speed difference above. It's 30,000. So you can put this number in here. 30,000 equals 13,600 times 9.8 times h. Okay, so that's it. That's how you do it. You get your h to be 0.225 meters when you solve there. If you want to know what we were doing before, what I was saying before is that the P on this level was not just P left. So I was actually expanding this side to say that this was P bottom, and I was putting an extra plus rho GH of the water on top of this side. So I was saying that the pressure up here is actually not the same as the pressure down here, which is true. The pressure is gaining as we go down here, but apparently we don't need to be that complex, and we can just say that that pressure is uniform on that side. Here you see the fluid on the bottom attached to a tube with a smaller area in the center and larger areas on the outside. The airflow is going to turn on. Now you see the water in the middle section where the area is smallest rises higher than the water on either other side.